Hi everyone, I am Sunaina Pati. I'm a grade 12 student from Guwahati, and today we're going to learn about projective geometry. This session is sort of like an introduction to projective geo. And before starting the actual class, here's some quick notes. So, although this class is essentially based on projective geo, elementary solutions are like really appreciated here and even in contests. And elementary solutions are basically angles, POP, lengths, if they're nice, and basically not contain any inversion or bash, etc. I personally have never solved the geo problem with using any of the advanced methods in real contests except Sharigan and IGEO. So, yeah, do use elementary techniques first and try to give feedback in it. Moreover, feel free to like ask any doubts anytime. Also, I might have technical glitches, so sorry in advance. With that, we'll start with like an elementary geo problem so that we tribute elementary geo so that the elementary geometry lovers don't feel any hatred. Yeah. Here's the first problem, which you guys have to try. I didn't say anything important or just introduction. You basically have to try that problem, which does not use any projective geo thingy. It's just a normal geo using elementary techniques. Is everybody fine with it?
Yeah.
Okay. Um, I'll give you guys 5-ish minutes or like take time. This should be solved. We will solve. Try it. Once you're done, you can raise your hand or like type in the chat that you're done, and we can start discussing. Also, there's like a diagram to it, so I'll just at least follow that too. Yeah. So basically, you have like two circles which touch each other at like a point A, and then you have BC chord of the bigger circle which touches the smaller circle at point K, and O is the center of the smaller circle. Now you have to show that BOC passes through the midpoint of the line segment AK. So we have 5 minutes. We can start discussing at 7:10. Yeah, and once done, you can just raise your hand. It's just solve it with normal synthetic techniques, which would include angle chasing and POP. Then hash if you want to.
How will you even bash this?
I really don't have any idea, but out of the box. Is it item level? Does it even matter where? No, it's not. I think it's probably it's not angle chase. Also, at least I don't know the angle chase solution. It's probably a good RM level problem if RMO would have existed. You guys can try it out. It's actually nice. A thing I can say is like you have tangencies and you have circles. You have like sort of three circles. So what do you remember? As in, like, what do you smell when you like see tangencies? Oh, am I supposed to speak loud? Oh, okay, sure. So you're given like tangencies, and you have like somewhat three circles. So what does it remind you of in general? Is what you're supposed to think. Yeah. So don't call me mom. Oops. Did anyone like solve it or had any ideas? You guys can share it. Like, please share it so it's interactive.
Oh,
It's okay. You can go ahead, Pranav.
no, it's nothing. I just realized it was wrong. I read the problem wrong.
It's okay. Should I like explain the problem? Did everybody get the problem right? Hopefully. Okay, I'll wait.
Yeah.
Okay, 2 minutes. Yeah, sure, sure. Like yeah, take your time. If you like close enough, I won't spoil it for you guys. But it's a nice problem to try. Okay. Um, Hold on, I think this is like anybody who's like close to solving the problem or a bit more of time. Okay, I'll speak thoda sa. So basically, you have tangencies and sort of like showing MOBC is a circle. So you have like sort of three circles. And when there are three circles, what's the best thing you know about three circles?
The radical axis mean data point.
Bingo. So think about radicals axis of like three
Yeah,
circles.
like the BOMC and the purple circle's radical axis just looks weird, no? That's the issue.
Mhm. I mean, radical axis and what is related.
Oh,
Uh,
wait, no, I don't think we really need radical axis, or
we
do we
don't.
need?
We don't.
Like, if,
That's just for motivation purpose. Like that's what I tried first.
yeah, makes sense. Also, if T is a radical center, then BCKT is minus 1, right?
If T is T,
Radical center, then BCKT minus 1.
BCKT minus one. Are you sure about that? Mm,
Am I missing it?
let's see.
Okay, it's not really true.
Like, why would yeah, so what are you trying right now, Pranav? If radical axis fails,
No idea.
What's somewhat close to radical axis?
I was thinking that OM passes through the radical center, but that's random.
Okay, wait. Did I actually dilute it so much? Okay. Um, Forget about radical axis. Okay, how do you prove radical axis theorem? What do you use when while proving radical axis theorem?
Like power of point. Take with circle 1, circle 2, circle 2, circle 3, and circle 1, circle 3 is equal.
So think about power of point if you
Yeah, I mean, like, I was thinking about power of point, but there is nothing good to think about that. No? Like, you
sure.
can think about power of M or power of
How about
K.
okay?
Like, extend AK to meet somewhere. That's
Mm-hmm.
also random, I
How
would say.
about okay? Let me ask other people's idea. Siddharth or Swastika or Anurag. Anybody has any idea? Or anybody else? Okay, so claim the radical center will be tangent from, which makes sense. Yeah. But as Pranav stated, how would you get the radical axis of the circle, the purple circle and the circle BOMC?
Can we like extend AK me to circle or somewhere and then we get like that's the midpoint of that arc?
Yeah, it is. It is the midpoint. Yeah, that's actually called the shooting lemma,
Yeah.
and it's somewhere like you can go on a very simpler road.
Oh, if the tangent at A meets BC at T,
Yes,
then OT, let's say, meets at OT will meet at M,
yes,
and we're trying to prove that OMBC is cyclic.
yes.
So then, and OT into OM, we just need to prove that
TO.
TO into TM is equal to AT squared, which I think is just true. Maybe.
Yes. Why do you think it's true? Let's ask anyone else, like someone else to like say.
I also think that
Um, Anurag, can you like be a bit louder? I couldn't hear that thing.
actually, I write my claim after chat.
Chat. Oh, so we need to prove. Yeah. Yes, you need to prove Tm into To is equal to Ts squared. Now there are various ways of proving that, but
It's just by similarity.
it's just by similarity,
Yeah, it's
and
just in that.
it's just similarity. Exactly. So I'll give the walkthrough if that's fine. Um, Let me go in. Um, okay, define the point Z, which is actually AA cap BC. So exactly what Siddharth said. And then you see what's the relation between Z, M, and O. Z, M, and O would be collinear because O is the circumcenter, M is the midpoint, and Z is like, so it's forming as an isosceles triangle, right? And then you get ZAO and ZMA similar because this is 90 degree and this is also 90 degree and you have this angle common. And then you finish it by POP. If anybody wants to see the finish of POP, let me just paste the solution over here. So exactly what Anuragan said. So it's ZB into ZC is equal to ZA square, right? Because ABC is circumcircled. And then ZA square is equal to ZM into ZO because of the similarity we got, and hence we got ZP into ZC equal to ZM into ZO, and we're done by POP. So yeah, this was our tribute to Oh, what's POP? Oops. POP is part of point. Yeah. In which, yeah, part of point. I call it POP, but in exam or anywhere in contest, just write. Do you remember the concept? Okay, so basically, I'll just quickly get an overview of what POP is. So, if you have uh, a circle and then you have quadrilateral A, B, C, D, so it's a cyclic quadrilateral, and say it intersects at K, then KB into KA is equal to KC into KD. And the converse of it is actually true. It's probably given in NCERT grade 10 textbook. Yeah. Anyway, so that was what our tribute to.
Where is it in grade 10th textbook?
It's there in grade 10 textbook. I'm pretty sure. Yeah, tangent second theorem.
I mean, they would have mentioned that xb into x equal to x into xt, but they don't tell x square minus radius square thing.
Then it might be an audition. Like, I'm pretty sure it was there.
It's not there. This is there. It's none of that.
I see. I see. Okay, then maybe audition. Anyway, so moving on. Since we are learning projective geometry, we should be very familiarized with the very famous point called the point at infinity. Okay, I see. Then it would be there in any just refer to I think chapter 2, chapter 1. I'll give the references to you after the class if that's fine. Yeah. Now, since we are working with projective geometry, one thing we should be very familiarized with is the point at infinity. Now, basically, what's point at infinity? So, have you ever seen the railway tracks? They look like they're converging. They're never like intersecting, but they're like sort of converging and converging. So here's the famous line from Igbo. It's not famous. I just took it off from Igbo. It's called "All parallel lines converge to the same point in the horizon." And you could imagine like this. This is like an infinite long railway track, and they look like they're converging to a point. So in Euclidean geometry, we have defined that parallel lines never intersect, right? However, in projective geometry, we say that the parallel lines do intersect at a special point called point at infinity, and for every class of parallel lines, that is, it's an equivalence class where two lines are in the same class if and only if they are parallel to each other. So for every class of parallel lines, there is a point at infinity. So what's a projective plane? A projective plane is basically the Euclidean plane only, but there are point at infinity for every class of parallel lines, that is for every direction, and the line at infinity, which is like the line composing of every single point at infinity. Quite heavy. Is everybody fine with what I said, or like just basically there's like parallel lines in Euclidean plane they do not intersect. In projective plane they do intersect at a point, at a special point called point at infinity. Isn't it hypothetical? What is line? First question is, ma'am, isn't it hypothetical? What does line at infinity is defined to be? Can you, oh, okay. So the second question, it's basically line comprising of all points at infinity. Because you have like all points at infinity and you're just basically having a line comprising of all points of infinity. And is it hypothetical? Uh, what should I say? We let's no, it's not hypothetical, or it is. it's quite, it's not hypothetical. Like if you see, if you follow Euclidean plane, it's definitely hypothetical. If you follow projective plane, it's not hypothetical. It sounds very fancy, but then you get somewhat used to it. So yeah. Pran, if you want to comment, you go ahead and
In real
comment.
world, I think it's hypothetical, no?
It is sort of hypothetical, but then every mathematician just does research on,
Yeah,
non-Euclidean
but like
space
that's how
time.
it's defined. But in real world, it doesn't exist. Nothing like pointed
I
infinity
mean,
exists, I think.
I really don't know how to comment on that question, but mind you. Let's anybody else who wants to comment if projective plane is hypothetical or not?
I guess it's defined.
I think yeah. Let's take it as hypothetical as of now. I'll just confirm it after the class. If that's is that fine? Hopefully. Okay. So basically, if you have two parallel lines AB and CD, AB intersection CD is point at infinity. This is point at infinity. P subscript infinity symbol. Another example is you have AD parallel to PE parallel to CF, and you have ABC parallel to line DEF. So they intersect at point. So ABC is parallel to DEF, and they intersect at point at infinity Z. And ADBECF, they're like parallel to each other, and in Euclidean plane we would define it as non-intersecting lines. However, in projective plane they do concur at a point at infinity called say y. Now this point at infinity and this point at infinity are those are two different point at infinities because they're different class of parallel lines. Is that fine? Like somewhat, if you're, is that fine? You're like getting the essence of what's point at infinity is? Everybody? Yeah, exactly. Due to direction, it changes. Do they intersect on both sides? Which one? We. Oh, okay. Parallel lines? Hmm. I haven't thought about it, but they intersect only at one point, which is fun. Interesting. Okay, so here's a short exercise for everyone to be comfortable with pointed infinity. Because when I first started out with um, projective geometry, I was definitely not comfortable with how projections worked with pointed infinity. So here's a short exercise. Given AB parallel to CD, define point at infinity as AB intersection CD. So it's somewhat like this. It's actually in both the directions, by the way. Just for convenience, just
And
take it.
like, how will it be both the directions?
It's
Because
hypothetical. Hmm?
it still can't be both the directions. Like, let's say if AB and
When
CD are there, and you say
mhm.
point at infinity in that direction on the two sides, then they technically intersect at 2 points, right? Which is not possible. Two lines can intersect at max 1 point.
The fact that okay, fine, let's assume it intersect at one side only. Which side would it be?
I mean, like, if you go too much
It's
towards the right or too much towards the left, you reach the
it's
same point,
you
no?
reach the same point. Essentially,
Yeah.
there's like only one point. There's
Yeah.
no sides, man. It's sort of like the longitudes, I think, of the Earth.
That's spherical geometry.
Yeah, that's spherical geometry, but it's sort of like similar to it, because they don't have a side. Anyway, so where would the what would be the intersection of E point at infinity cap omega? Any idea? Like how would you make the point of intersection of E P infinity and omega. Pranav, Siddharth.
Reading.
Oh, wait 1 second. Swastika, you were speaking probably. Take the antipode of E. What is omega? Omega is basically the circle. Ma'am, won't it be tangent? No, it won't be tangent. Which one would be tangent right away?
I think EP infinity should be tangent to omega.
No. It might be if E is a nice point, but in general, how would you define? Swastika, you were saying something, but I couldn't hear it because your voice
No,
was
I
low.
wasn't saying anything.
Okay. So basically, this point E point at infinity cap omega is basically the line. So consider a line which passes through E and you intersect, and that is parallel to AB and CD. And yeah, this is E pointed infinity cap omega. Is so is that fine with everyone? Like why this is E pointed
Yeah.
infinity cap omega? Everybody? Okay, clear.
Yes.
Yeah, cool. Now the next thing, which is like probably the one which you're waiting for, is a bit of theory and defining what cross ratios are. Okay, so cross ratios are basically defined for circles and lines, and then it gets extended to conics if I'm not wrong. Don't take me over there because even I'm not sure about conics. So for the lines, you have 4 points. So given ABCD collinear, the cross ratio of ABCD is CA by CB. This is the ratio like but so CA by CB is to DA by DB. So that's basically like CA by CB into DB by DA. Moreover, we use the directed lens over here. This is the definition. Is everybody fine with the definition?
Yes.
Ma'am, are they in same sequence? Yeah, they should be in the same order. If that's what you're meaning. Yeah, they should be in the same order, A, B, C, D. That's how you have defined. So that's how cross ratios are defined. And we use directed lens. There's like two reasons why we use directed lens. Actually, one basically. When we say ABCD, so that's basically for the uniqueness of the cross ratios, which would be useful after a certain period of time. So we'll come back to it later. The cross ratio is sort of like a function which takes 4 points and gives a number. You know, this is like distance and distance and then distance. And we can also use the point at infinity in the cross ratios. Like cross ratios, points can be anything you want of the projective plane. So here's an example just to get familiarized with the cross ratios and the definition of it. Oops. So if you have AC equals to 4 centimeter, BC is 5, DA is 18, and DB is 9 centimeter, find the cross ratio ABCD. Just to get comfortable with cross ratio, I just put this question. Also use directed lens. once a person is done, you can like just tell the answer and we can proceed.
-2/5.
-2/5.
Yeah.
Yeah, it is -2/5. Oh, sorry. Yeah, it's -2/5. So basically, you have CA by CV is to DA by DB, and CA, if you assume CA is +4, then CB is in the opposite direction, so we'll get the -5. Then we have DA going in the same direction, +18, DB going in the same direction, +9, and then you do the manipulation, you get -2/5. Everybody fine with this? Siddharth, Swastika, Anurag, Anush, everybody? I assume yes. Ma'am, wait, but when we say CA, but when we say, it means cross ratio. Yeah. Order of points, no,
Doesn't, right? Like you just do
the
AC
way
build.
I defined, ABCD, that would give the, like, that would do like CA by CB is to DA by DB. Now, if you change the order,
No, I mean the
as in
order on
if
the
you
line.
change,
Like in the this
order on
line.
the line, then
Yeah.
it won't. Yeah, then the
Yeah.
inner thing would also change according to the order you give. Anyways, let's not confuse them. The next is defining cross ratios for this points lying on circle. Now, obviously, you can't use directed lines over here. So you have plus minus according to whether the segments intersect or not. So, yeah. Let ABCD be points lying on a circle. Then ABCD, the cross ratio is defined as plus minus CA by CB is to DA by DB, where it's plus if the segments AB and CD do not intersect and negative otherwise. That's the definition. Everybody's fine with it, right? Like, you basically have 4 points lying on a circle. If everybody is fine with it. Yeah, moreover, here's something you guys should remember. If you have 5 points, which are like collinear, or it also works for the cross ratio, or the points lying in the same side, same circle. So you have like, if you have ABCD, cross ratio is equal to cross ratio of ABED, then we get C equals to E. It's quite helpful when you do harmonic chase. So just keep that in mind, that cross ratios are sort of like invariants and unique. Thank you. So if you have like 3 points given, and actually never mind here. This is fine with what, like this is fine till now, right? Okay. Yeah. Next is a pencil and perspective. So we're coming to the projection part of the projective geometry. Anyways. So, oops. So here's the thing. If you have ABCD as 4 points lying in this order, ACBD be 4 points lying in this order in a line L, and you have a point P which is not lying on line L, and then take another line, say N, and consider the intersections and call them A dash, C dash, B dash, D dash. Then you have ABCD, the cross ratio of ABCD, equal to the cross ratio of A dash, B dash, C dash, and D dash. This theorem is like the base of the projective geometry, and it's quite easy to prove. So I'm just going over the proof, and you guys can actually try it on your own. The proof basically uses a lemma called the ratio lemma, and the ratio lemma is basically like if you have triangle ABC and then you have a point D, then BD by DC is basically AB by sine of DAB by sine of DAC. It's proved by 2 times of sine law and then manipulating it. So you guys can prove it on your own after the class. I'll just repeat what's happening. So basically you have the cross ratios being preserved whenever you're projecting from a point P to another line. So from one line to another, when you project it, the cross ratios are preserved. Is that fine till now? Oh, you want to note? Yeah, go ahead. Okay. Also, what do you mean? Tell the procedure of the proof again. How about, okay, I remember what I said, ratio lemma. Now I won't say the procedure of the proof. Like you can go with it and try it again on your own later. And if you don't get it, you can tell me. But yeah, it's basically two things. So you use the ratio lemma and then write the cross ratios independent of the ABC. Yeah. Moving on. This whole configuration is denoted by PACBD. Actually, it's denoted by, yeah. Oops, it's denoted by PABCD. It's denoted by P and then cross ratio of ABCD, just because you're like there's a perspective from point P, you're projecting it from point P to different lines, and the cross ratios are always preserved. Right. So in math terms, yeah, just remember this. This is like the foundation of projective geometry. Like everybody just writes this. So you say the cross ratios are equal. How are the cross ratios A, B, C, D and A dash, B dash, C dash, D dash equal? Now because you're projecting it from point P, like projecting it from point P from the line M, sorry, this was line L, to line M. So from line L to line M, and the cross ratios are preserved. Is that fine? Like there's nothing fancy, you just like define the mathy symbol. Is that fine with everyone? We just defined a lot of stuff. So is that too heavy as a definition or? I'll take that as a yes then. Listen, you guys can actually be comfortable and speak out. Just don't be shy asking random doubts. And if you're not comfortable sharing your voice, then you can use the comment section. No, wait, yeah, comments. Similarly, so here we did lines to lines. Now we'll do circles to line and vice versa, which is like pretty cool. Now, remember this perspective thingy? We're taking perspective at point P. Now, perspective, you need a point P so that you can project, right? Here, circles to lines also, you need a point P so that you can project the bundles, right? Now, the only condition imposed on the projection is that point P must lie on the circle. So I'll just quickly show the diagram. You can't project from point P if you're like projecting from a circle to a line. You need the point P to be on the circle so that you can project from a circle to a line or from a line to a circle. Here also the cross ratios are same. So the cross ratio A, B, C, D and A dash, B dash, C dash, D dash is same because point P lies on the circle. Is that fine with everyone? Like the way I explain, or should I re-explain? It also works for Phoenix, yes, it does. Like in general conic, yeah. Like I'm not very sure about that but I have heard it's working and I have seen also. Anyways, so here are the various diagrams of how projection works, and yeah, this is my favorite lemma, which I think you guys should definitely try it out. I call it the concurring chords lemma, but yeah, just prove it. So it's very fun to prove. So if you have 4 points lying on the circle in this order, so A, B, C, D, and you have a point P inside the circle. So here's the point P, and then you consider the intersections of A, B, C, D with the point. So you consider PA intersecting with the circle, PB intersecting with the circle, it's intersecting at F, PC at G, and PD at H. Now prove that the cross ratio of ACBD and the cross ratio of EGFH are same, very equal. Everybody got the problem statement? Yeah. Cool. Pranav, Anurag, Siddharth, Swastika, Atul. Okay, cool. There are other people also. I hope you guys are also fine with it. Yeah, you got the problem. Okay. I'll give you guys good amount of time to try because this is like a nice problem. Okay, I'll give you guys 5 minutes to try and then I'll give the first hint. Everybody fine with it? I'll take that as a yes. So yeah, okay, fine. I'll drop the first hint at 7:52. Everybody fine with it? It's a pretty good problem. So I think the first step is converting the cross ratio thing to the way we define cross ratios and then think what's enough to prove and then go backwards and then you'll be done. It's like very elementary. So don't think of anything fancy. No need of introducing any other points. Yeah. Yeah, you have something to say, Anurag. You done?
Yes, I guess.
Okay, go ahead.
So if ACBT is equal to EGFH, then ABCD is equal to EFGH.
Mm-hmm.
So we can use the previous lemma you told. We can extend all the sides and we can draw two lines on the both sides. We can easily get that they both have the same cross ratio from our perspective P, because they lie on the same lines PA, PB, PC, PD. So we are done.
Mm-hmm. Wait, what? Can you repeat it again? Say,
Okay, so I was telling if ACBT is equal to EGFH, then ABCD is equal to EFGH. It makes sense for the ratios you
yeah.
might say. Then we can convert AB cross ratio of ABCD to by extending PA, PB, PC, and PD, and just making a line through it so that it
Wait, so you can't do that, right? Because P is not a point lying on the circle. Yeah, it's fine. Just don't use projectors here. This is like the theorems which which are used in projective geos are basically like length dash, like length or cross rate, like length or ratios, but smart ones. Anyways, time for me to add the first two part of the walkthrough. It is like which two cross ratios do we have to show are equal? Obviously, ACBD and EGFH. So you just convert them into the two fractions getting multiplied by the form. And then this is the major hint. I really don't want to spoil it, but I did spoil it. Note that BA by EF is equal to BP by BE. BA by EF is basically BP by BE. By similarity, of course. So try it. And if you guys don't get it in like, if we don't proceed in like 4 more minutes, then I'll give the solution because we need to proceed to other parts. Or actually, you know what? Just try it as much as you can. And do let me know if you have any minor progress. So the hint I gave was BA by EF equal to BQ by BE. Um, this Scott theorem. What's this Scott theorem? I actually laugh for the same reason. Um, this is the chord theorem, right? Yeah, we're proving that theorem. Which theorem? Are you talking about POP? This is not POP. Like POP, we're not proving POP. Anyways, so the cross ratios you have to show equal are basically you have to show BA by BC into DC by DA. You have to show it's equal to FE by FG, right? Yeah, into HG by H. Exactly, yeah. this. And then you take everything to the right side. Here it would be 1. You have to show this. You take everything to the to the left hand side here. So basically you have to show the product of those stuffs is 1. And then use this fact. BA by BF is equal to BB by BE. Anybody that has any progress on how they're using the second hint can tell me if they have any progress. Mm. Okay, Pranam, did you have any progress on this? Mm.
Not really. I was trying to use similarity somehow.
Mhm. Okay, what happens when I take it to the right hand side actually? Sorry, to the left hand side. When I take this to the left hand side, I get BA by BC into DC by DA into FG by FE into HE by HG. And you have to show this is equal to 1. And think about it. We got BA by FE. DC is somewhat so think about it. BA is sort of closely related to EF because A is going to E, B is going to F. So it would be nice if I keep BA and FE together. So BA by FE. Now DC is going to HG. So I'll write DC by HG. The FG. FG is over here. FG is going to BC. So I'll write FG by BC to HE by DA. You have to show this is equal to 1. Now can you guys proceed? Oh, yeah, exactly what Anurag wrote. Yeah. But then it can be even more clever. Like like the next step would be finishing it. So you want terms to cancel out so that you get to 1. And remember how you solve these length thingies. You want something to appear twice, once in the numerator, once in the denominator. Show diagram, please. Yeah, definitely. Like the last hint was actually just saying try some
We
manic.
can use another similarity to like dt by hf is equal to dp by
Should I write what you're saying, Anurag? Yeah, go ahead.
we can use another similarity using two lines. Like I like to use two consecutive lines. You can take two lines at the one line between them and use this. Then we get dp by. Can you show diagram so I can tell it's happening? Yes. Then we have dp by ph is equal to dp by pf.
So dp by
dp by ph is equal to sorry, dp by dh is equal to pf by pp. And this is what we needed. Then we have a combination of each other in ratios. So we are 10.
I see. So you're saying dp by PE into
Nor PP by PF is equal to not PE.
oh PF. I
Yes, yes.
see. Yeah. Wait, why is here PF by the way?
You can see that BP and F is collinear.
BPF is collinear. Yeah, so
So we can use similarity here. Like then we can get BP by PF is equal to
we have
PH
here.
by BP. Wait, let me write it in the chat.
Yeah, sure. Anyways, so BP by PF is equal to PH by DP. Okay, so what do you do next? Actually, it's just not that complicated. Just think along the same direction. This is VP by PE, and you want stuffs to cancel out.
Can we use FG by BC is PG by BP?
Can you repeat?
Like
And
FG by BC is PG by BP.
so I can't. Is my mind? Wait, can you like
I
say
have
the
sent
bit?
the proof in the chat. Can you check?
Yeah.
Yes,
And
it's a-
Anemika, can you like say it a bit louder?
Yeah, like FG by BC.
HG by BC.
Yes, FG.
Oh, F. I think you're saying F because that's a nice ratio. FG by BC is equal to
PG by BP.
um, PG by
BP.
BP. Yep, that is it. FG by BC is equal to PG by BP. And then you get anybody else who wants to say which two ratios would come here in terms of P and some point.
Should I go ahead?
Yeah, you can go ahead.
Okay, then we will have DC by
DC by HG.
yeah, that will be what should be PD by PG?
Okay, good work. PD by PG
And what's that? This is PD by PD. Like HG.
by PD. Exactly. And it cancels off and you get 1. Like this cancels off because there's a numerator and a denominator and they cancel out and they give you 1. And this is what you wanted to prove. But this was the famous concurrent chords lemma. Everybody fine with the proof of how it's happening? Okay, okay. I'll add the proof in case anybody has any doubt. You guys can just go over it also. So we need to show this, right? That was the cross ratios, and we took this to the left-hand side. We simplified it, just manipulated it a bit, and then we used the similarity. BA by EF is equal to BP by PE, and we use it everywhere. So BA by EF is equal to BP by PE, BC by HG is equal to PD by PG, and so on. And it gives us 1, which is what we wanted to prove, and we're done. Yay. Here's the next problem, which is sort of well known. It's called the butterfly theorem. And yeah, it says you have a chord AB, you have the midpoint M, and chords ZW, XY pass through M. Now you consider the intersection of ZX and WY. This is P and this is Q. The theorem says that M is the midpoint of PQ also. That is what the theorem says. And yeah, this would probably be the last problem we'll be doing. Like this is very, very, very nice. So just try it. It's full projective and a bit of ratios. So it's since it's a hard problem, you guys can try. No contest problems. I had a lot of contest problems, but we're like running very, very slow. Just very slow. So it's fine. We'll hopefully have a part 2 of this and I can cover close there. If Abhiraya doesn't mind. Yeah. I'll give 10 minutes so that you guys can think about it. And I'll give the first hint in like 8:15. And yeah. By the way, how many of you have like seen the proof of butterfly theorem? Either the synthetic or the projective. Either one works. Anyone?
I've seen the synthetic in like step
Anamika, I can't hear what you're saying.
I think I've seen the synthetic proof in like step another.
Mm-hmm. I see. Anybody who has seen the projective proof? Yeah, yeah, exactly. A beautiful geometry has like synthetic proofs. It's a pretty good book, so yeah, do try it. But it has hard problems like APM 2019 P2. It has even harder problems. I think it has an IMO P3. Which one? 2008 or 10? I'm not sure about that. Yeah. Like that, I think it was for Monge, if I'm not wrong. Like there are way harder problems. Even the Serbia problems of ABGT, which is like hard. Anyways, here you have three projections, like two projections, and basically normal ratios. So think about it. I think the projection idea is like quite nice. So you guys would love it if you like find
It's
it.
the projection idea by taking M as a perspective.
No, not M. In fact, M would be a point in the bundle. Like, be projecting. Oops. So I didn't give the first hint, but you sort of want to have ratios conditions involving P and Q. Because your ultimate goal is to prove P, PA is equal to QB, or you want to prove PB equals to QA. So you sort of, since it's a projective geometry class, and then you sort of want some ratios involving P and Q. And as I said, it would also involve M because projections from M would be easier. Think about it. Which projective bundle would I consider? Also, we'll use the. No, we won't use anything else here. So you want to involve M, right? You sort of want to involve P and Q because you want ratios involving P and Q. and then you're having a circle. So you want sort of like two circle points. Or no, your wish. Just find a bunch of good projection which would give you some sort of relation between Q and P and A and B. Think about the points. Like the good points in this theorem is A, B, P, Q, and M. So you sort of want a cross ratio which involves A, B, P, M, and Q. Got it. And if anybody has like any idea of which projective bundle they like considering as of now, you can just speak up and that would help other people do so. Yeah. MYQB and MPAX. That's not the exact. That's not the projective order, but the projective bundle you're considering in the group. But you're kind of like close on thinking which bundles they are. It's sort of asymmetric, kind of. Like I'm getting so much hints. And even anybody else who's like considering any projective bundle as of now and has failed or is on process. Okay, how about you consider the bundle
AMPB.
MPP or in better you consider the bundle ABPM. I'll write it in the chat so that nobody's confused. Oh, wait, I have a stylus. I can write it in the. Um, get this. Consider the bundle A, B, P, M. And now you sort of want to involve Q also. Yes. You want to relate it. You want to relate Q with A and you want to relate Q with P also. So any idea which projections you should consider?
Shadow.
We can
Projection and shadow.
consider
Which shadow? Wait, Pranav Malay, can you guys repeat? I didn't hear that clearly.
we can project at Z, like ABPM goes to ABXW, and then we can project at Y. So ABXW goes to ABMQ.
Yeah, exactly. So you basically get ABPM is equal to ABMQ. And that's actually a nice one, Pranav. Like my proof involved projecting from X and Y. Z and W are not involved. Wait, I think hold on. My one
It's
had
the same, no?
X and W. Yeah, it's the same exactly. It's the same. So that was the first part. You had to prove that the cross ratio ABPM and the cross ratio ABNQ they're equal. Now, what do you get from this though? You got the cross ratios. You know how good cross ratios are. Now, use the formula of cross ratios, like which was presented. before. And what do you get from it? Now you get PA by PB into MB by MA is equal to MB by MA. Sorry, this is MA by MB into, did I write it correctly? Yeah, I did. Just Q by QA. Not what we want to. Did something wrong over here, but okay. Yes. We will find it once you guys are done with it. Anyway, so yeah, we got this one. These ratios to be equal. Now anyone has any idea what we get next?
It just choose the formula, right?
It's just what?
The formula of cross ratios.
Yeah. So what do you get from that?
Right? You use the formula and use that MA upon MP's minus 1.
Mm-hmm.
Okay.
Should I write that? But
Yeah.
okay. So we get that.
PA by PP,
Mm-hmm.
MA by MD.
MB by MA. And this
Yeah,
is
so this is MA by MD,
MA by MB. And then
QP by
QB.
QA,
And then MB by MA is what?
minus 1.
It's 1. And A by MA is also 1. So what do you get? PA by PB is equal to QB by QA. Anybody? Okay, so how would you finish it off? You're like very close. There's a very famous thing which we use in algebraic manipulation, but you can do the same over here. What do you want to show? You want to show that M is the midpoint of P and Q. How would you show that? If you show that PA is equal to QB, you would be done, right? If you show PA is equal to QB, you would be done. Or if you show PB by QA, that PB is equal to QA, you would be done. Right? You just have to show these two lengths are equal. How do you get this thing from this? Like it's actually close. Actually, you don't even need anything. This is like if P and Q are like satisfying this thing, Then obviously M is the midpoint because of symmetric thingy, but then we're just proving why it's happening. Take projection from X and Y. We can add 1. Exactly. Yeah, great. Exactly. So we can add 1 to both the sides. Now when we add 1 to both the sides, that is PA by PB plus 1, essentially the same, right? But PA by PB, I'll take 1 as PB by PB, so this. And then I'll take 1 here as QA by QA. And this would imply that AB by PB is equal to AB by QA. And this would imply that PB is equal to QA. And this is how you prove butterfly theorem using projective. Yeah. Did everybody get what we did, or should I repeat? I'll just paste the proof so that you guys are clear with it. So Pranav did it in the other way. Pranav projected from Z and then Y. But it eventually gave us this thing, which was the most helpful. So we get ABPM cross ratio equal to cross ratio of ABMQ. And then we use the cross ratio formula to get this thing. PA by PB is equal to QP by QA. And then, as Manoj said, we add 1 to both the sides and we get this, which implies PB is equal to QA, which implies M is the midpoint of 2Q. Yeah, this was the proof of the butterfly theorem. The next thing is introducing harmonic bundles. So I'll quickly introduce what's harmonic bundles and what's harmonic quad. So at least we can say we have done projective zero. Oh, by the way, everybody is fine with the proof, right? Anurag, Maler, and everybody else?
Yes.
Yay, okay. Okay. So next we have introducing the harmonic bundles. There's nothing fancy when it comes to harmonic bundles. You just have the cross ratios equal to -1. That is it. To both. Anyways, so if ABCD are 4 collinear points in this order, and then if ACBD cross ratio is -1, then ACBD is called an harmonic division or a bundle. That's it. So ACBD is the cross ratio is -1 if and only if BA by BC divided by DA by DC is equal to -1. Simple. That's how we define cross ratio. Now here's the interesting properties of why harmonic bundles are so famous. How many of you are familiar with inversion? Anyone who knows what inversion is? Yes, great. So the how should I say? Yeah. So if you have ACBD, ACBD -1, that is their harmonic. It's same as saying you have a circle with diameter AC, and B and D are the images of are the inverted image with respective to the circle with diameter AC. Let's say what. So when we construct the circle with diameter AC, we get that B is the image of D when we do the inversion. So AC, BD is -1. That's how we define. And moving on, going with the same definition of how we define this, this will prove it later of why the cross ratio here is -1. We can also, there's also like sort of a very good harmonic bundle, which is AB M point at infinity, where M is the midpoint of AB and point at infinity is the direction of the line AB. So this you can imagine sort of like AB as the diameter of the circle AB, and M is the center. Now, when you do inversion, the center goes to the point at infinity. If you have heard that, so right, we haven't defined. No, yeah. So the center of the inversion, it goes to the point at infinity. So that's how you sort of relate inversion and projectives here. Also, here's a very cool fact. -1, so cross ratios of these all are the same. And you can try it on your own after the class. Yeah, that is it. I'll do till this and we can cover it. Is AB is the square of the radius. Yes, that's correct, Manush. So I'll take class till here, and we'll start with the harmonic quadrilateral in the next part 2 of this class. Is everybody fine with this? I hope it's fine. Like whatever we have covered till now. I'll ask personally. Malay, Anurag, is that fine? Like whatever we have covered till now? Yeah, cool. Okay. Great. Should I move to the harmonic chord or okay, let's try harmonic quadrilateral also. Okay. So ABCD are 4 concyclic points lying in the same order, just like this. And you have ACBD, the cross ratio of ACBD is -1. Then ABCD is called an harmonic chord. So remember this thing. This is like a very important thing, and it's used so much. Like they give you given a quadrilateral whose product of the opposite sides are equal, then they then stay the rest of the problem. And then when you realize, oh, the product of the opposite sides of the quadrilateral are equal, that immediately implies that ABCD is harmonic, provided the quadrilateral is cyclic. Right. So the quadrilateral must be cyclic and it satisfies this. It's harmonic. And when those cyclic quadrilateral is harmonic, it has so much of so many properties that you would be amazed, which we'll probably cover in the next class. Yeah. So this was harmonic quadrilateral. This was defining harmonic bundle, and it's sort of related to the inversion, as pointed out by Manoj. And then we proved butterfly theorem. We also went and proved the concurring chords lemma. Please don't forget this lemma. It's like one of the most useful lemma in the projective geometric aspect. We also saw centers to line and vice versa projection. Here, remember the point must lie on the circle. Like it cannot be inside, it cannot be outside. By the way, here we took the point to the inside. You can also take it to the outside in this concurring chords lemma. Over here, we just took projection from one line to another, and it preserves cross ratio. And then, yeah, before that, we defined cross ratios, and we discussed how point at infinity works, and we had one problem done. So now we did 3 problems, I think. Yeah, that's it. Thank you. I'll stop sharing. Any questions, by the way? After this, since we actually covered all the theory part we had to, we're done. And the next part we'll be doing fully problems. Like I actually had problems for this session too, but we were like quite slow. So we'll do it in the next part. So we had this, say them in a list. The well-known property is like I don't know how to define well-known, like name the well-known properties, and then we had perpendicular angle bisector lemma, which was then followed by some more problems. Oops, that's a cat. Yeah. This was the first contest problem. Actually, everything was shadowing problems. So yeah. Will we have another class? Actually, yes. I would request if Abhivaya agrees, then we'll have another class on projective geometry. I'll continue what from where we left today. And I hope by that time the YouTube video would also come out, so you guys can just revise also.
Yeah, that's definitely possible. Should I end recording now?
Yeah, sure. We're done with the class. That's all for